So hi everyone. So today we have Oliver Porth, who is working as an associate professor at the Anton Pannekoek Institute for Astronomy of Amsterdam, and who will present his work on the various states of black hole accretion.
Right, yeah, thank you very much, Raphael, for the introduction, also for the kind invitation. Yeah, it's a great pleasure to talk about this topic I've worked on more and more over the last years in this audience. So this is work done and done and with and by Jibor Musoko, my postdoc. Matthew Liska, of course, is a provider of great ideas. And yeah, we also talk with Michiel van der Klees, Adam Ingram, Nicholas Katz. I have 2 slides from work that he submitted recently. He's a student of Sasha Tchaikovsky, and yeah, also discuss a lot with Bart Rippada. There's many more collaborators in this larger collaboration called the Event Horizon Telescope. I want to briefly talk about like the accretion state of Event Horizon Telescope targets, which you know, Galactic Center and M87. And I'd like to also point out the larger HAMR and BHAC collaborations that make all of these kind of simulations possible. Right, so this is one of those seminars more on the high energy side. So we are really interested in like what goes on around compact objects. So why do we care about compact objects at all? Well, we know that compact objects will hold up a key relationship with star and galaxy formation, right? So black hole feedback is what really is a key ingredient in shaping galaxies and the universe how we see it today. This is all done, this kind of feedback is done through the process we're studying, like the process of accretion and jet formation. And that's really what we want to like really understand. But also, of course, around compact objects, you can probe more. You can probe fundamental gravitational physics, right? Because we can probe gravity and really strongly curved regions of the space-time. That's quite unique around compact objects. So we want to like unlock this laboratory, and also very similarly, we can probe fundamental physics of dense nuclear matter. So if you think about neutron stars, these are the densest objects that are not black holes in the universe, and you can really probe a unique region of the dense nuclear matter phase space that you have no chance of getting a hold on at Earth and at like terrestrial accelerators, because you have not only dense matter but also relatively cold matter, something that you cannot really generate in a hadron collider, for example. Right, so simple things like measuring mass and radius, the equation of state of neutron stars brings you quite a good step forward in this endeavor. And of course, we're all interested in origin of cosmic rays and high energy emission, which has something to do with processes around these compact objects as well. Right, so we really care about that. And how do we probe that? We probe compact objects mostly when we see them. We see them really, really brightly when they do accrete. So what do we see then? What's the kind of data we're trying to like get the mysteries out of? We're looking at spectra, of course, right? So we see them across the entire electromagnetic spectrum, like broadband spectra and line spectra, which hold quite some interest and some information. There's other things like spectral timing, so we can really see processes around X-ray binaries happening on rapid time scales, so we can there's a lot of information in the timing and really the noise process. Already the noise of the signal tells you quite a bit. There's aperiodic variability and there's also periodic variability. I'm going to that later as well. Of course, polarimetry and lags between different components to allow you some kind of dissection of the system. Right, so how do we interpret all of this data? It's really not easy data, it's quite complex. It's like not an image, like as you're used to in astrophysics, but it's relatively abstract data. So you need really good models that you can trust, and you think the physics is in set models, and then you see what do these models generate and compare it to the observations. So there's essentially 2 approaches here. So you can rely on geometric and like semi-dynamical models where you put some of the physics in. Maybe you use some scaling relations, and you can solve things like in a one-dimensional fashion, for example. That gives you quite some freedom to explore large parameter space. So that's a very nice approach. But if you want to really harness all the especially time variable nature of the observations, you really have to go to dynamical models. And what do I mean with this? So we want to put in as few parameters and assumptions as possible. Of course, there's always assumptions about the initial conditions and geometry of things. But we want to do that as little as possible. We want to also focus on the physically realizable models. So basically we put in all the physics equations that are sensible, and then we see what actually can be realized out of that, and to contrast this to like more simple theoretical models as well. So this is of course time dependence, which brings us to essentially radiative general relativistic magnetohydrodynamic simulations we're carrying out these days. Okay, what is the grand challenge in this game? What do we really want to understand about like this black hole accretion process? I think the grand challenge is really this kind of diagram, and really understanding accretion throughout all of its states, and also understanding like state transitions. So what is that? If you observe an X-ray binary, so here's one black hole X-ray binary called GROJ1655, and on the top figure I'm showing the X-ray luminosity. So these are X-ray emitting sources, right? You can come to this conclusion if you just look already at the kind of Stefan Boltzmann black body temperature of these objects. So X-ray binaries radiating the X-rays, right, and they go through this kind of outbursts, and this whole thing takes maybe a couple of months, sometimes a year, and an X-ray binary would dramatically brighten up. At the same time, it changes its spectrum also dramatically. That's shown in the lower panel. That's called the spectral hardness. And this is really just like optical astronomy, where you do like a U minus V. You might remember this is essentially a hardness where you compare the counts of the flux in two different filters. And here we just compare the hard band over the soft band. So when the spectrum is very high and highly energetic, you call it hard, and otherwise you call it soft. If you plot these two things against each other, you come at basically the Hertzsprung-Russell diagram of X-ray binaries. So we plot luminosity versus hardness, which is kind of luminosity color diagram, right? So, and you see that over these time scales, a source does a quite funky loop in this diagram, which is called like a turtle head diagram. So it kind of has this hysteresis. It goes from quiescent. I don't know if you see my mouse. I don't actually see my mouse a lot. It goes up from a quiescence in the hard state, where it can like linger for years. It will go up and make this cycle, and at this, when the accretion rate increases, and then also transition in the spectrum over. So while all of this happens, many things change in the source, and for example, jets, which you see initially, will eventually switch off, and and then the source kind of goes down as the accretion rate drops eventually. So to understand all of this is really important if you want to understand like when do black holes feedback. So when do you actually increase their luminosity? When do you launch these jets, or when is it winds? Because you want to understand like how much energy do these objects give back to the galaxy? What is fed back in terms of radiation? What is fed back in terms of kinetic energy, and so on. So what triggers all of that? That's kind of the grand scale challenge here. There's a little bit more in the light curve as well. I mentioned this earlier. So you actually have this, if you look at the light curve really, really closely on quite short time scales now. So before I showed you the light curve on years, essentially time scale. If you now focus on processes of a few seconds, there's actually quite a lot of information in the light curve as well. which allows you to probe actually the turbulent processes as the disk is cooking, because it's cooking on the seconds, milliseconds timescales. So you kind of see the noise process. In the noise process, you see actually turbulent processes. So that's basically the broadband noise of the power spectrum density. But often you also see very distinct features in this noise, which are called quasi-periodic oscillations. And there's a lot of taxonomy with these QPOs. I don't want to really go into this. Just want to point out that there are so-called low-frequency QPOs that range around 30 hertz or below 30 hertz. You call them low-frequency QPOs, typically around maybe 10 hertz. And then there's also a relatively rare variant, larger than 30 hertz, sometimes around a couple of 100 hertz, or 100 to 100 hertz, called high-frequency QPOs. And yeah, this is something the disk does. The disk actually starts oscillating with these frequencies. We really want to understand, like, yeah, what can we use this for kind of the seismology of the disk? What can we actually extract from these oscillations? And there's a lot of theoretical work that has tried to do that. And since we're doing dynamical simulations, we want to really see what of those oscillations, what of those models actually can be realized with the assumptions we put in. I have one more slide on these QPOs. So QPOs are really connected to these state transitions. So if you go from the hard to the soft band, so from the right on this plot to the left, you see that the so-called type C QPO actually changes in frequency. It actually increases in frequency. So what goes on with the disk and the spectral transitions is actually really linked to, like, the oscillation of the disk actually changing as well. So we want to, yeah, the idea is, like, we need to kind of understand this kind of in tandem. And ultimately, if we understand the mechanism, we can use this as a diagnostic tool. Can we use it to learn something about the disk, or to measure actually things we're really interested in, like black hole spin? So there's many spin measurements based on spectrum, right, of iron lines, for example. And they all come with quite a few uncertainties. So it would be really nice if we have some robust way to do this alternatively. Okay, I think the first thing I want to talk about in this kind of diagram, so I'm showing this schematic just symbolically now. This is the turtle head we've seen before. So the first stop I want to make is actually in the state where galaxies spend 90% of their time in, which is the kind of the low hard state. So, and also our galactic center NM87 are essentially down there. So what are the peculiarities of this state? So it's not feedbacking a lot of energy, but it's basically the ground state of galaxies. So, and it's the state in which we can really see into the really heart of the black hole, really close into. So what are the salient features here? At really low accretion rates, so you can imagine if your density goes down, collision rates, which go as density square, right? So you have to have the probability that an electron hits a proton, so it's a density square process, like colliding between two particles. That means as density goes down, the collision rate goes down quite dramatically. And if we're in this really low density, low accretion rate regime, you have to start worrying about, like, things not really colliding efficiently, which means we have to talk about non-thermal or kinetic effects. Just to set the scale a bit, if you think about Sagittarius A star, a typical Larmor radius of a particle would be 3 kilometers of a proton, which is of course much smaller than the Schwarzschild radii, so that's fine. But the mean free path of such a particle is on the order of 10 to the 15 centimeters. So basically, now we are in a situation where the mean free path of this particle, of the proton, is much larger, at least mean free path along the magnetic field. It's much larger than the system size. So we really have to start worrying about that the fluid approach will kind of break down, right? Because that's what you say, your mean free path is smaller than your system size. And then you're good in a few fluid approximation, but this is not really valid in these really low luminosity sources. And the effect of this, the first effect of this at least, is that you decouple electrons and protons. So electrons will not collide enough with the protons that get the viscous heating before they fall into the black hole, essentially. And they actually will have lower temperatures. So this is an old diagram, it's quite illustrative, by Narayan et al., where you have the temperature on the y-axis and the distance on the x-axis. So you can see in this model for such a star, electrons and ions essentially decouple at around 1000 Schwarzschild radii, essentially. And then you can see how the electrons are actually colder than the ions. The ions follow essentially a 1/r profile, right? Like a virial temperature profile here. The electrons are actually colder than that because the electrons can do the radiative cooling. So we're really dealing with a 2-temperature plasma here, and this is essentially the difficulty of modeling low luminosity sources, I think, because we have to step out of the fluid approximation that works so well and add something in. Right. Yeah, one more step on this. So how can we model this 2-temperature effects? So the process you have to think about is that we have viscous heating, right? This is accretion. So we have a Q plus. So we typically say this is viscous heating. Electrons radiate. So there's a Q minus here in the net heating rate, which gets subtracted. And then you have this collision operator that tries to couple electrons and protons again together. So this equation will give you the same temperature, the same heating rates when you're very well coupled. And otherwise, it depends how much of the viscous heating electrons actually receive. This is famous delta parameter. So not only do electrons radiate, they also receive essentially less of the viscous heating. So this delta parameter is smaller than 0.5. It maybe is 0.01 or something on these lines. So that's an effect you have to now basically add into GRMHD. So what is this delta parameter? How much of the viscous heating do the electrons receive? And there's whatever you put in there will really matter for the radiative efficiency that you get out of these systems. So here on this plot is the radiative efficiency for various deltas. So not only do electrons cool, electrons receive less of the heat, and the accretion flow is radiatively inefficient. And it's also this delta parameter that makes the electrons even colder, making radiative efficiency even lower. So, and I think Ilek had raised his hand. So Ilek.
Yeah, is it okay if I interrupt
Yeah,
for a
sure.
question? Or,
Maybe
okay, sorry about this.
later, yeah.
So I'm not exactly sure I fully understand what this delta parameter represented, this viscously dissipated heat. Is it like purely kinetic, or is it also like in terms of deposit of electromagnetic energy being dissipated?
So so this Q plus parameter is quite famous in accretion theory. That's basically the viscously dissipated heat. So basically, if you go from one shell to the inner shell, you have to basically, there's torques acting to do that. And if you basically take the energy that these torques, the work that these torques actually do on the accretion flow, if these torques are viscous, like with an alpha prescription, then you will find out that together with this accretion torques, there's a heating associated.
Okay, so that's purely a fluid viscosity aspect.
Yeah, that's in this picture. Yes, this is fully that, and then the delta just is a factor in front that you put there. And of course, doing fluid, we don't really know what this delta should be.
Okay, thanks.
So we have to borrow information from somewhere else. Yeah. Okay. Yeah. So that's basically the extra little bit that comes in here in this very low accretion rate regime. And let me go on one more slide. So other than that, we are actually quite well served with a relatively simple set of equations. So we can safely ignore the radiation force. Also, radiative cooling is, for the BHT targets, relatively unimportant. So we can get away with general relativistic MHD equations, just a vanilla type, which I've just given you once more here. And then there's a low accretion rate regime. You can optionally add one additional equation that takes care of the electron heating. Right, so this is an equation for the entropy of those electrons, and there's again this little delta parameter that actually you have to borrow from kinetic physics, right? So that really depends what you put, what kind of subgrid physics model you put. So typically expresses delta as a function of plasma beta or sigma, and then you go with it, right? You have to really do kinetic simulations to kind of come up with what delta should be. But yeah, so this is basically what's in the EHT workflow, essentially, and these low luminosity sources. The spectrum in this regime is looking like this. So this is Sagittarius A star spectrum. We are having like thermal electrons, which do synchrotron and inverse Compton emission. I've highlighted that bump here, and the whole thing has a real nice sub-millimeter bump, so like left of 10 to the 12 hertz or so. You see that the spectrum really peaks, and this is where the Event Horizon Telescope observes. So this is due to this, essentially due to the thermal electrons, right? So that's the dominant contribution that is important at this 10 to the 12 bump. So modeling those properly is really important for the EHT. If you want to model the source at other wavelengths as well, because you might want to step away from the horizon, and you see that actually if you want to understand really the jet as well, you have to follow this curve of the non-thermal electrons, because they start to be important in the gigahertz frequencies where you can see the system at larger scales. Of course, it's more important for M87 where we have a real jet, but also like in the infrared, you'll start to need to care about the non-thermal electrons as well. So only 2% of energy is probably needed in these non-thermal particles, but like in certain wavelengths, they are really important. Right. So yeah, so let's try to like look at this system at different scales. Here's an effort we've done with actually zooming out from this is M87 now for a change, trying to zoom out from there and seeing like, can we connect also to these larger scales? Well, if we put in some non-thermal particle prescriptions here. So what we have done here, we have actually assumed that the particles are not thermal, as you have in this Maxwell-Deutner distribution here with the relativistic Maxwellian. And actually they have a power law tail. And again, this power law slope is then informed by like subgrid models of assuming that there are reconnection areas in the jet. So there's kind of a plasma beta and sigma dependence that tells you what the slope of these particles then should be. Right, so this is a subgrid assumption. Let's just see how far we get with that. So this is then the spectrum that you get by just adding these non-thermal particles. Let me see if I can go through that. So there's a thermal spectrum for, let's focus on the red curves. So if we just have thermal particles and we go to larger scales and we start seeing more and more of the jet, right, so you actually underpredict the intensity. If you just have thermal particles, if you have like a mixture of these non-thermal particles, you actually can explain the spectrum quite well over 10 orders of magnitude, 5 orders of magnitude. So that's quite nice. So really, to explain the spectrum, we need those non-thermal particles, as we know. But you can also go, of course, go a little bit more because we do large-scale simulations. So we can also look at the morphology of the system. So GMVA, so that's the source that the global millimeter array that looks at the source at these scales of maybe 1,000 Schwarzschild radii, shows this kind of morphology. So this is M87. It has this kind of limb-brightened structure here. It's quite broad actually, and nowadays, like, can we explain this structure? And the answer is relatively well. So this is like probably the best fit dynamical GRMHD model of that recovers basically the shadow of the black hole as well as the 1,000 Schwarzschild radii structure. So this is a highly spinning, magnetically arrested disk, right? So we can also do some cuts. Basically, look at the diameter of the jet. So this is a relatively broad jet, and then you can see that, yeah, the highly spinning, magnetically arrested, so we have really strong field lines on the black hole. These kind of models are favored, right? So there's probably still not enough edge brightening, so we might need to think about extra in situ particle acceleration at these in this shear layer. But yeah, that's the current state of affairs of this game. So yeah, so by adding like subgrid electron heating prescription and subgrid electron acceleration prescription, I think we are doing a reasonably well job explaining these low luminosity sources meanwhile. And of course, these sources are still around, so we can improve those models over the years. I want to go on to something else now. I want to still walk along this diagram, going into more high accretion rate regimes. This is I want to start with a so-called soft intermediate or soft state, which you find around here. So at high X-ray luminosities, you actually have a thermally dominated spectrum. You don't really observe any jets anymore, but often like equatorial winds, as well as so-called type C QPOs. And if you are in a higher state, even these high frequency QPOs we briefly mentioned. So this is how the spectrum looks like. Here you have a relatively nice accretion disk black body that you can fit, and this is then the hard component, which is really low. So this tells us that the disk goes probably all the way to the black hole, making a nice black body spectrum. So what are the model ingredients if you want to model the state? So luminous disks are optically thick, right? So they are radiatively inefficient, radiatively efficient. That means they're optically thick, and that makes them also geometrically thin because they cool efficiently. So they decrease their scale height, and radiation is of course essential. Yeah, adding radiation to these models is not exactly easy. And there's now two dominant approaches of this. I think the one that's still very widespread and is actually not doing a terrible job is a so-called noble cooling scheme. So we actually use thin disk theory to cool this disk to a target scale height. So we can dial in essentially what is the scale height we want. It has the advantage that we can actually dial in the scale height that we can numerically resolve. And then we just use very simple thin disk theory to kind of set this target or compute this target temperature. So yeah, basically very simple thin disk theory says the sound speed is disk scale height times the Kepler velocity. Temperature is P over rho is around sound speed square. So for a given like aspect ratio, I directly know what is the mid-plane temperature that this disk should be at. And then you use a cooling function that kind of dials in this. So this is of course, very, very crude, but that's actually the way how you can like maintain thin disks. If you don't add this cooling function, essentially you have viscous dissipation going on all the time, so the disk will actually like puff up. And if you don't remove this energy, you actually end up with a thick disk very quickly. Right, so I'm going to show some simulations that have this prescription. but the more more novel or somewhat more rigorous approach is actually so-called the M1 closure scheme, which means we actually recover some of the radiation physics in form of this radiation tensor. So we have our matter and electromagnetic energy conservation here. There's a source down on the right-hand side, which actually describes how matter and radiation couple together. Right, so if you add these two together, you have 0 on the right-hand side again. So we of course have total energy conservation, but this tells you how much emission you have out of the matter into the radiation field. Right, so there's basically the radiation physics enters here. That's your emission and absorption right there. And then we also evolved this radiation tensor. Oh, there's a new too much. It's only a 2 tensor, which is obtained by moments of the intensity. So you have your energy, you have your radiation flux, and you have your radiation pressure. Right. So basically, you treat the radiation as a fluid, which is, not terrible. So you can talk about its flux, you can talk about its pressure, but you cannot really talk about its spectrum, and you cannot really talk about what happens if fluid velocities collide, you get a shock. So that never happens to radiation. So there's really something funky going on if you have crossing rays in this approximation. They don't just pass each other. So that's kind of the limitations of the method, but of course you can at least talk about various basic things. So the first model I want to discuss, like in this luminous accretion regime, is work done by Jibbo Mosoke. It's maybe the biggest GRMHD simulation so far. We want to model the soft state, and in the field actually this is done by assuming a topology of the magnetic field. So if we want to have the disk go all the way to the black hole, we know we can achieve that if we have a purely toroidal magnetic field and no vertical magnetic flux. And also in the soft state, we don't observe any jets. So if we want to target this, we already put in, there's no vertical magnetic flux going through the black hole, a purely toroidal magnetic field configuration. So we use, and we use this cooling approach to cool the disk to this 0.02 target scale height. This is a very thin disk still, needs crazy resolution to still resolve the MRI on this disk. And where we think we can apply that model is kind of here, the soft intermediate state, where the disk is still thin, it's not slim yet. So that's what we're trying to model. And on top of this disk, this disk is tilted. There's very little constraints about the geometry of accretion stream, where there's a spin axis in X-ray binaries. So they could actually be substantially tilted. We really don't know, but the question is now, what does it do to the accretion disk dynamics if you have that? So this is a volume rendering of that simulation on the left of the density field. And there's a cut through the density on the right. So this is of course doing very intricate dynamics. This very strong tilt does a lot to the to perturb the flow here. You can see, for example, that from time to time there is an inner disk is kind of tearing off of this. Right, the whole disk is doing precession, so you see slowly the outer disk moving around. Right, this is due to the Bardeen-Peterson torques from the black hole spin. It's kind of trying to torque the disk. It's trying to torque the disk into alignment, and it actually reacts to this by precessing, and the precession frequency of this disk is given by the lens tearing torque over the angular momentum in the disk. So if this torque is very strong, stronger than you can viscously transport through the accretion flow, then this disk will actually tear off, and that you see actually happening cyclically quite often. And then once you're torn off, you see actually the inner disk, which has much less angular momentum, is precessing quite a bit faster than the outer disk. So this is quite intricate dynamics, and we would like to understand a bit more and see if this maybe has something to do with what we observe, and things like QPOs really come to mind. Right, so, first thing that you can see, analyzers basically analyzes kind of tearing events, and tearing, like looking at the phase and the tilt of this disk. So this is looking at the two angles as a function of the radius. One is the tilt angle, which is the angle between the z-axis and the angular momentum of a local ring, some radius. And the other one is the phase angle, which describes how far this angular momentum has precessed. So you can see that there is like discontinuities in the tilt angle, which means that there is actually a tear, and then the inner disk tilt angle becomes smaller and smaller from the inside out. So this is actually Bardeen-Peterson alignment, which tries to align the angular momentum and the spin. And at the same time, this tearing radius gets smaller, and the outer disk kind of accretes back in and replaces this inner torn off disk until the whole thing actually repeats again. So this is quite intriguing now. So we see that this tearing happens cyclically. Each cycle lasts for a few seconds, and this inner subdisk precesses then with the lens tearing frequency. So if that happens, and you look at the radius of that, we get a precession of 3 hertz essentially. So you have the solid body precession that you can see nicely here. So around 5 times you precess, you reaccrete the outer disk, and then the whole thing can repeat again. So if you think about the low frequency QPOs, the type C QPOs, the observed QPO might actually be an addition over many of these tearing cycles in the soft intermediate state. So, and you always look at the disk basically from the side, and sometimes you look at the precessing inner disk face on, and you get a lot of flux, and sometimes edge on you get low flux. So that's then how these precessions translate into the light curve. That's the idea. But there's actually more in this here, so it's actually quite nice that you can actually look at. We just used the mass accretion rate as a proxy for the X-ray luminosity, and we basically made a Fourier transform for every radius, which is shown here, and we overplotted over this is the various like frequencies. So this is the Keplerian frequency, this is the epicyclic frequency, and then steering precession frequency. So as the disk tears, you get a strongly pushed signal here at the radial epicyclic frequency of the tearing radius. So basically, the inner disk actually starts to oscillate radially, does some kind of breathing oscillations with the frequency given by the tearing radius. And this is really nicely in the regime of a high frequency QPO. So this tearing can maybe do two things for you, which can do the low frequency QPOs out of precession, and it could do the high frequency QPOs out of these kind of disk oscillations at the tearing radius. So this was m dot. You can go one more step further. I can ray trace these signatures, which was done by Andrew West, a student of Henry Kawczynski. And he actually took the dissipated energy out of each from the simulation, and basically turned this into emitted radiation. And then if you do this and analyze this light curve, here's another X-ray light curve. Really, this is not m dot anymore, but this is really the synthetic X-ray light curve you see strongly pushed. This is the epicyclic frequency at around 97 hertz. At the tear, this is basically it's 2 times harmonic, and also there's a funky 3-to-2 factor there as well. And here, if you have a bit of faith, you actually see this low frequency QPO signal at around 3 hertz from the precession. So yeah, this is quite nice stuff. You can really start translating these really complex simulations into things that we do observe. But there's actually quite a bit more in the simulation. So recently, Nicholas Katz analyzed the simulation. This is this same simulation, the very strongly tilted disk. And there's quite a few things that go on that are not really covered in standard accretion theory. For example, you see extreme scale height variations along phi. You can see it already somewhat in the side view here. So if you go around the orbit, actually the disk expands and contracts twice. And there is a contraction point 90 degrees to the line of nodes, where actually the orbits of the plasma kind of meet and collide. So that's nicely shown here. So this is basically a sky map. So this is theta and phi for a shell, and you can see how the density of the disk really expands and collapses. And there is this kind of interaction point that Nicholas called like a nozzle shock. So yeah, as a function of as an effect of this warped accretion, you get these scale height oscillations. What do these do? You can really go into measuring like standard things. For example, the alpha viscosity parameter, which we know in MRI is essentially in MRI turbulence, which is essentially dominated by the Maxwell stresses, which you can write down like this: BRP phi, so the magnetic stresses over pressure. This is like your Maxwell stress alpha parameter, and that's typically a number that we can't really get much above 0.1. So in these simulations, you have Maxwell stresses are like 0.03, 0.02, 0.01 perhaps. That's just as much as Maxwell stress give you. But if you actually compare this to what is the angular momentum attached to matter, so the effective alpha essentially, so this is the mass flux times u phi, so this is actually the angular momentum transported by the matter. And this normally needs to be generated by some kind of torque to kind of balance this ingoing mass flux with its angular momentum. This effective alpha is way off the Maxwell stress, so it's even larger than 1. So this is really not an alpha disk. So there's something that really is outside of thin disk theory that needs to be invoked to explain how these effective alphas are so large. And we argue that it's actually the nozzle shock. So Nick analyzed this very, very closely, and if the streamlines come together, there's actually dissipation happening here. And it's not, this time it's not the dissipation of the MRI, of the torques, but it's really the dissipation of the shock that can actually locally get rid of quite a lot of orbital energy. So he estimates that in this nozzle shock, there's around 1.8% of the orbital energy lost. And it shocks and then it's radiated out. And that can actually also drive this accretion, this really effective accretion that we see in the warp disk. Right. I want to still have some discussion, so I want to go quickly into the hard intermediate state. So this is really where the action happens. So you still have, well, you have high accretion rate, right? But you also still have a jet, and that's of course important. So you have a high accretion rate, and that of course means that you also have, if you have a jet, you might actually have a lot of energy still in this jet, and then this jet switches off as you go over to the soft intermediate state over here. But what are the features of this state? We have a thin disk and something that we like to model as a hot ADAF-like flow. This is a standard diagram, so it's kind of this truncated disk structure, and then the dominating model is that the transition rate just kind of moves in as you go to the left. And so this disk is thought to be truncated, and at the same time we still have some jets. So how does this truncated disk form? This is one simulation that is we built to kind of look at this particular state where we actually have a thick disk that has a lot of magnetic flux, which we then cool to this target temperature. The thick disk actually is able to move in a lot of magnetic flux, which is initially like seeding the black hole. But now that actually the disk cools, and this is also thought to happen during the state transition, that, you know, the disk collapses and the thin disk actually can't keep all this flux on the black hole. So what has to happen is that the flux kind of moves out of the black hole. And you can see that, yeah, these vector potential isocontours, so these flux surfaces actually move out of the black hole and actually truncate this disk at larger radii. So this is kind of a magnetically arrested disk analog for the thin disk. And so that is a simulation that is running for maybe 100 years or 20 seconds or so for an X-ray binary. And it illustrates this formation of this kind of truncated disk structure. So what is the dynamics of this truncated disk? So the idea is that you have this really nicely arrested disk, and has some large scale flux going through the disk, and it's really quite reminiscent of having like a Brentford Payne mechanism. So you can have actually some wind that is launched from this strong magnetic fields going through this inner disk. And so we're thinking we are kind of in this state here. So what happens then? So as the disk collapses, the magnetic field threading the black hole leaks out and forms this truncated disk. And then a couple of things can actually happen. So the strong magnetic field quenches the weak field instabilities. You still have accretion through like Rayleigh-Taylor modes and like spiral modes. And the strong ordered fields, however, also launch like magnetic winds. Actually, the wind actually takes quite a bit of the angular momentum out as well. And these winds actually take also matter out, so they drive the density down. And as you know, if you drive the density down, you run into this regime where you actually electrons and protons might actually not couple so efficiently anymore. So you actually might run into a 2-temperature decoupling just from the fact that this wind actually takes away so much matter outwards and decreases its density as it does that. So we actually should be ending up with hot electrons and even hotter ions, basically like in this Adolf state that I discussed very early in this talk. And the conjecture here is that this is maybe the corona. But this is still a conjecture because this is done with this noble cooling prescription, so we can't really talk about energy transport here. We can't really talk about energies and temperatures of electrons, because there's really not a self-consistent energy equation being solved here. So more recently, this simulation was essentially restarted.
Oliver, so can you like wrap up in within a few minutes?
Yes.
Thanks.
Yeah, I'll wrap up in like 2-3 minutes. Very good. Yeah, I just want to illustrate like, you know, this next step in this game where we actually then restarted the simulation using like a praise allocation that we got. We restarted the simulation with the M1 closure and also 2 temperature effects. And this is basically comparison between the GRMHD and the GR radiation MHD. It looks relatively similar. And the whole thing is scaled to 0.35 M Eddington. This is contrasted with the case where you don't have any large-scale poloidal magnetic flux. So there's actually no wind, there's no magnetic truncation, and there's kind of a soft state source here where the disk makes it all the way to the black hole. Right. So what is the processes that go on in this like magnetically dominated like truncated region? Since there is 2-temperature thermodynamics now, you can actually talk about this kind of coronal plasma here. So you have to look into this white contour. So this is all matter that's kind of lifted off the disk. And it has temperatures, which we now can talk about, of like 10 to the 10 Kelvin for the ions, which makes a lot of sense. So this is like a virial temperature. This is just what you have around a compact object. Another question is, what temperatures do the electrons have? So remember, the electrons do the cooling. The electrons don't receive as much heat from the viscous processes, or any heating process mostly. So the electrons are cooler, but they're still like significantly hotter than the disk. So they are like 5 times 10 to the 8 Kelvin or so. And then the conjecture here is that actually these like 5 times 10 to the 8 and 9 Kelvin electrons are actually what makes the corona. So they significantly inverse Compton cool, but they're still like hot enough to explain the hard upscattered spectrum from the inverse Compton. So it actually could be that this, what we're seeing here, might actually be the processes that make up the corona. That's, I think, quite interesting. So lastly, yeah, I want to wrap up. So just after all of this, I think doing the simulation is quite accessible these days. I mean, doing this really, really thin disk simulations are really quite expensive. Not so accessible, but actually you can get your hands dirty and like start simulating these GRMHD flows. And so the codes are really available. So the one I wrote is the so-called BHAC code. It has quite a nice documentation with a tutorial which guides you through like doing this black hole torus simulation with different adaptive mesh refinement levels. I'm happy to help you with like setting this up. Then I have a couple of technical slides. Maybe this is for discussion, but I think we're hitting the hour. So maybe you want to ask me something about like that. So I picked a technical topic that really is always coming up in this these simulations, which is the poles. And the poles are killing you really because they are invoke very, very small time steps next to being just geometrically very difficult to deal with. They actually make your time step go down as a function like resolution to the -2. So if you increase your resolution, like your linear resolution, your time step or your simulation cost goes actually to the 5th power as a number of cells in one direction. So that really is killing you. There have been a number of things designed to kind of circumvent this problem. Yeah, I'm happy to discuss a couple of them. I'm mentioning solidification, de-refinement, using Cartesian coordinates or other coordinates as well. So I'm not really going to cube spheres. But I think I want to like jump to the takeaways. Yeah, and I can just leave them here, and maybe we can discuss some more if you have some questions. So I'll leave that just open for you now. Okay, thanks.
Thank you.